Good day. Today we are going to introduce the third chapter in our course. This is chapter 22 in the Giancoli book, and it's on Gauss's law. And Gauss's law is an important consequence of Coulomb's law, which we talked about in chapter 21. And it has some important applications that we'll talk about. It certainly makes certain problems a lot simpler, and we'll demonstrate that in a little bit. And it's also one of Maxwell's equations, and we won't quite get to Maxwell's equations in this course, but it's one of the foundations of the study of electromagnetic waves, and so that'll carry on in Physics 3. So let's talk a little bit about Gauss's law and setting it up. The first thing you need to talk about when you're talking about Gauss's law is the concept of electric flux. So electric flux is a measure of the component of the electric field that is penetrating through a surface. So the surface has an area A, and the electric field is crossing through it. The electric field vector makes an angle theta with the line drawn perpendicular to the surface. So we're measuring the angle drawn relative to a line that's perpendicular to the surface because it allows us to take advantage of the vector dot product. And if you remember from Physics 1, the dot product is a scalar product. So electric flux is a scalar product. And if you have a constant or a uniform electric field acting on a flat surface, the electric flux is equal to E times A. So the magnitude of the electric field times the area of the surface times the cosine of theta, where again, theta is the angle that the electric field vector makes with a line perpendicular to the surface. In more general terms, so if the electric field is either not uniform or the surface is not flat, or both, you need to resort to calculus to figure out the electric flux. So in that case, the first thing you do is you figure out the dot product between the electric field vector and a differential element of area. So you would need to figure out the differential element of area in order to solve this problem. And then you would integrate over the surface. So the differential vector dA, again, the direction is outward, or is points out of the surface. And and the magnitude, I don't know if you've done or how much you've done as far as integrating surfaces goes. But if you've done anything with two-dimensional integrals, you have an idea of how the differential element of area works. And we'll talk a little bit about that. We'll show an example in a couple of minutes. But for now, we'll do a relatively simple example as far as calculating the electric flux. So this problem states that a uniform electric field of magnitude 5.8 times 10 to the 2 newtons per coulomb passes through a circle of radius 13 centimeters. So what is the electric flux through the circle when the face is perpendicular to the field lines, and when it's at 45 degrees to the field lines, and when it's parallel to the field lines? So let's illustrate this. And so we'll get back to our trusty whiteboard. And so we'll make this the plane of the circle. So in the first case, the lines are pointing perpendicularly outward. All right, so the perpendicular to the field lines. And so E is perpendicular to the field lines. And so that's E. And so you draw a line perpendicular to the plane of the circle or to the surface, and you see that theta is equal to 0. And when theta is equal to 0, the cosine of theta is equal to 1. So this is the circumstance when the electric flux is maximized, when the electric field is pointing directly through the surface. So that the electric flux in this case is equal to E times A. And you don't need to worry about the cosine, it's simply 1. And so we are given a magnitude of 5.8 times 10 to the 2 newtons per coulomb. So we can write that as 580 newtons per coulomb. And you want the area of the circle, so that's pi times, and the radius is 13 centimeters. So you would write that as 0.13 meters, and you're squaring it. And so you plug those numbers in. And you get 31. And so the units of electric flux are 31 Newton meters squared per coulomb. So that's the electric flux in the first case. Now in the second case, we have our line that's perpendicular to the surface, and we're told that the face is 45 degrees to the field lines. So the electric field is pointing at an angle. And so in this case, and theta is equal to 45. So if it's making an angle of 45 degrees with the face of the circle, it's also making an angle of 45 degrees with the line that's perpendicular to the plane of the circle. And so maybe the best way to set this up would be like that. Okay. So this is 45 degrees. And then this angle is theta, but theta is also going to be 45 degrees. They're complementary angles. So the electric flux is equal to E times A times the cosine of theta. And we already know what the product of E times A is, so we don't need to write all that out again. That's 31 Newton meters squared per coulomb, and you're multiplying that by the cosine of 45 degrees. And so you do that, and you get 22 Newton meters squared per coulomb. And so that's the electric flux when it's at an angle. And then the last thing is the face of the circle is parallel to the field lines. So in this case, the field lines go straight across the face of the circle. So they're completely parallel. And remember, the electric flux is a measure of the component of the electric field that points through, or excuse me, that crosses through the surface. Well, in this case, no component of the electric field is crossing through the surface. And so you can say that theta is 90 degrees because, again, you have theta is the angle that the field lines make with a line perpendicular to the surface or to the face of the circle. And the cosine of 90, of course, is 0. But conceptually, you can see that as well. There is no electric field crossing through the surface, so the electric flux has to be 0 in this case. And so that's how you evaluate the electric flux in the specific case, uniform field flat surface. Again, if it's not uniform or the surface is not flat, you need to be a bit more creative than that. But that's what we have. So now we are going to go back to how this applies to Gauss's law. Now, Gauss's law is a direct consequence of Coulomb's law. Gauss derived it from Coulomb's law. And it's very useful for a number of applications. And like I said before, it's one of the equations Maxwell used when he was developing his theory of electromagnetic waves. And again, that's something that you'll learn about in Physics 3. But Gauss's law applies to fully enclosed surfaces. So not a flat circle, but rather maybe a fully enclosed sphere, a fully enclosed cylinder, a cube, something three-dimensional rather than something two-dimensional. And you're only interested in the surface of that three-dimensional object. And from a mathematical perspective, there doesn't have to be a real three-dimensional object or a physical three-dimensional object. You can just imagine the surface and evaluate the electric flux into or out of that surface. And this equation or this relationship will apply. So the electric flux is equal to, again, the integral. And if you notice the integral with the circle in it, that's either a closed surface or a closed loop, depending on whether it's a one-dimensional or a two-dimensional integral. But the electric flux through a completely enclosed surface is equal to 4 pi times k, the Coulomb constant, times the charge, sign included, of whatever is inside it. So what happens is the electric flux only depends on the charge that's inside it. It does not depend on any charges outside the surface. And it also doesn't depend on where inside the surface the charges are distributed, whether it's a point in the middle, whether it's uniformly distributed throughout, whether it's some sort of random distribution. It totally doesn't matter. And an equivalent way of writing this is, instead of 4 pi k times the enclosed q, you can write it as q enclosed divided by epsilon naught. So we're introducing a new constant, epsilon naught, which is equal to 4 pi k. And epsilon naught is equal to 8.85 times 10 to the negative 12 Coulomb squared per Newton meter squared. And that's called the permittivity of free space. And so it's the fundamental electrical constant. And when we get to magnetism, we'll introduce mu naught, which is the permeability of free space, which is the fundamental magnetic constant. And their values in SI units depend on the definition of the ampere. But what we'll find out, again, when we get to Physics 3, is that the product of those constants does not depend on how you define the ampere. And in fact, it depends on one of the fundamental constants of the universe, which you will learn about soon enough. But epsilon is equal to 1 over 4 pi k, and conversely, k is equal to 1 over 4 pi epsilon naught. And in some circumstances, it's easier to work with k. In other circumstances, it's easier to work with epsilon naught. In general, with Gauss's law, it's easier to work with epsilon naught. So let's look at a problem that's more conceptual than mathematical. And this will illustrate something about the basics of Gauss's law. So the total electric flux from a cubical box 28.0 centimeters on a side is 1.84 times 10 to the 3 Newton meters squared per Coulomb. What charge is enclosed by the box? So we have, getting back to the whiteboard, we have a cubical box, and so we have, well, it's not the most cubical looking cube, but we'll go with it. And so it's 28.0 centimeters on a side. And all three sides have that shape or have that dimension. And again, it's not the most cubical looking cube, but I apologize for that. And the electric flux is 1.84 times 10 to the 3 Newton meters squared per Coulomb. So .84 times 10 to the 3 Newton meters squared per Coulomb. So that's your electrical flux. So we know what the electrical flux is, and we know the dimensions of the cube. And what we are asked for is what charge is enclosed by the box. Now, we don't know anything about where the charges are enclosed by the box. We just know that the box is enclosing charges. So from Gauss's law, the electrical flux is equal to the enclosed charge divided by epsilon naught. And before I go any further, I want to introduce a sign convention, or talk about an important sign convention. Signs, positives and negatives don't matter really if you're talking about a flat surface, but if you're talking about a fully enclosed surface, the signs do matter. That if the electric flux, or if the electric field is pointing into the surface more than out, then the flux inside will be, or the flux through the surface will be negative. And if it's pointing out more than in, the flux through the surface will be positive. And so this goes back to the last chapter. The electric field points out of a positive charge and into a negative charge. And so if you put a positive charge inside here, you would expect the electric flux to be positive. And so that's what that means. And so a positive electric flux means that the net charge enclosed is going to be positive. And that means that the field, at least in general, is pointing out more than in, depending on whether it's a simple charge distribution or something complicated with positive and negative charges involved. But that's the important thing. Positive enclosed charge means a positive electric flux. A negative enclosed charge means a negative electric flux, or at least the negative net charge means a negative net electric flux. But anyway, we can solve for this very easily. So Q enclosed is equal to the electric flux, which we've been given, multiplied by epsilon naught, which is a constant. And so that's equal to 1.84 times 10 to the 3 Newton meters squared per Coulomb, and you're multiplying that by epsilon naught. And so epsilon naught is 8.85, and this is in SI units, times 10 to the negative 12 Coulomb squared per Newton meter squared. And so you see the Newton meter squared terms cancel out, but only one of the two Coulomb squared terms cancels out. So you'll get an answer in coulombs. And when you do the math, you get 1.62 times 10 to the negative 8 coulombs. And that's the total charge enclosed inside the cube. Now, it could just be a point charge in the center of the cube. It could be a point charge at any different location within the cube. It could be uniformly distributed within the cube. It could be a combination of positive and negative charges with a net value of 1.62 times 10 to the negative 8 coulombs. It could be any one of a number of different things that gives a net charge within the cube of 1.62 times 10 to the negative 8 coulombs, and the electric flux through the surface will be exactly the same value in all those cases, provided the enclosed charge is the same. So that's part of the power of Gauss's law. And you can exploit that in some complicated charge distributions, provided the charge distributions are symmetrical. You can exploit Gauss's law to turn a very complicated integral problem into a relatively simple algebra problem. And so that's what we're going to spend the bulk of today's lecture doing. And so I'll show you how integrating to find the electric field works with these first two examples. And then I'll show you how Gauss's law makes them much easier. And then we'll go to a third example that's be much harder to integrate even than the two examples that I'm going to show you. And we're not going to go through that integration, but we can see how Gauss's law makes the problem doable at this level of physics. So we're starting with an infinite line of charge. So we're looking at distance r from a line of positive charge of infinite length, and a constant charge per unit length lambda. So how does this look? And we're going to do it the long way first. And it's worth it, it's instructive to see how the integration applies. And these are relatively simple charge distributions, so you may not think it, but as integrals go, this is relatively simple. So here's your line of charge. We'll define a point as the center, and it's infinite, so it goes an infinite length in both directions. We're evaluating the electric field at a point P, which is a distance r, or a perpendicular distance r, and we'll call it capital R to avoid some confusion. So a perpendicular distance capital R away from the line. And so we're going to put it in the positive x direction. So we'll set up xy coordinates to do this. So you have the line pointing in the x direction. And so we are going to look at a point, on the line of infinitesimal length width dx. And it's the vector, and we talked about this last time, the vector r points from a differential element of charge to the point where the field is being evaluated. So we will define its x coordinate is of this, in this case would be negative x, because I've drawn it to the left of the origin. And so how does this look? So remember the general equation for the electric field, if you need to integrate, is equal to dqs divided by r cubed. And we're going to use the second version of that integral because I think it's more instructive here, and I think it's easier to do it here. So in order to do this integral, we need to figure out two things. We need to figure out what this vector r is, and consequently figure out its magnitude. But then we also want to figure out what dqs is. So that's the element of charge. So we know we're looking over an infinitesimal element of length, and that the charge per unit length is lambda. So therefore, dqs is equal to lambda dx. So each of the charges on this line are source charges. They contribute to the electric field. So the differential element of charge is equal to lambda times dx. So now we want to figure out what the r vector is. So you look at this, it's got a component in the x direction, and it's got a component in the y direction. So we're going to write this in unit vector notation. So in the x direction, and so the magnitude is equal to the length. So the x component is the distance from the charge to the origin. And then the y direction is from the origin up to the point where the electric field is being evaluated. So the y direction is simpler. It's always going to be capital R. And so it's going to be something I hat plus capital R times j hat. But what is that something? So what is that x distance? Well, you define x as the distance you are relative to the origin, but to the right you're positive and to the left you're negative. So on this side, on the left side where we are, the x coordinate is negative, but the vector is pointing to the right. And when the x coordinate is positive, the vector is pointing to the left. So if your x coordinate is positive, your vector is pointing in the negative x direction. And if your x coordinate is negative, your vector is pointing in the positive x direction. So the x component of the r vector is negative x. Let me rewrite that. So it's negative x I hat plus capital R j hat. So that's the r vector. And that's what goes in here. And then you want to find the magnitude of this vector. Well, that you find from the Pythagorean theorem, that the magnitude is equal to the square root of negative x squared, which is simply x squared, plus capital R squared. So that comes from the Pythagorean theorem. So that's the magnitude of this vector. So now we can set this up. We have E, and there should be a K here for the Coulomb constant. So that term we need here. But K is equal to 1 over 4 pi epsilon naught. Again, the relationship between the Coulomb constant and the permittivity of free space. So we want it in terms of epsilon naught. It'll make things simpler, and we'll see that as we go on with this problem and the next one. So 1 over 4 pi epsilon naught. And so we can bring that out of the integral. And so dqs is lambda dx, and you're dividing by, and so the magnitude of r cubed, so we can write that as x squared plus r squared 3/2. And then that's equal to negative x I hat plus r j hat. And so that is the integral that we're evaluating over, and we're evaluating x from negative infinity to positive infinity. So how would you do that? And you can look look this up on an integration table if you need to, but the easiest way to think about this is to define an angle theta so that x is equal to r, capital R, times the tangent of theta. So you have x, which is the coordinate down here, and it's equal to capital R times the tangent of theta. Again, opposite over adjacent. Now, we're going to want the differential of that. So dx is equal to capital R. Capital R is a constant. The differential of the tangent of theta is equal to the secant squared of theta d theta. Okay, so that's the numerator here. The denominator is in the denominator you have x squared plus capital R squared. So that's r squared tangent squared theta plus r squared, which is equal to r squared times 1 plus the tangent squared of theta. And if you remember your trigonometric identities, 1 plus the tangent squared of theta is equal to the secant squared of theta. And if you don't remember that, this is, you can write 1 as cosine squared over cosine squared. You can write the tangent as sine squared over cosine squared. So that becomes cosine squared plus sine squared over cosine squared. So that's, in the cosine squared plus sine squared is simply 1. And so that becomes 1 over the cosine squared, which is equal to the secant squared. So now we can plug these values in. So we can bring the lambda out. And at positive infinity, the tangent of theta is pi over 2. And at negative infinity, the tangent of theta is negative pi over 2. So we've made a substitution. And we need to change the values we're integrating over. So dx is r times the secant squared of theta, d theta, divided by, and so here's where it gets interesting. So we have r squared secant squared of theta. We're taking that to the 3/2 power. So that becomes r cubed secant cubed theta. And then we have negative r tangent theta I hat plus r j hat. Now here we're going to do something a little bit tricky. We look at the I direction. And you see here that when you're to the left of the origin, the vector points to the right. The electric field vector points to the right. And when you're to the right of the origin, the electric field vector points to the left. Those are going to cancel each other out. So you can evaluate this integral in the I hat direction, but if you're going to get 0. So, I mean, you can do that if you want, but in the end, you're going to get 0. But everything, every point has a component that points upward. So the upward components are going to add together. But let's simplify this a little bit. So we have lambda over 4 pi epsilon naught. And so that's negative pi over 2 to pi over 2. And so we're going to break the integral in two. So we have, and I'm running out of space, I realize. So we have negative r squared over r cubed. So that becomes negative over r. So we have secant squared over secant cubed. That's 1 over the secant, but that's just the cosine of theta. And you're multiplying that by the tangent of theta. So that's just the cosine times the sine is just the sine of theta d theta over r, and that's I hat, plus, again, you have 1 over r, because of the r squared divided by r cubed. So you have 1 over r. And here, you don't have this tangent term, but it's still secant squared over secant cubed. That becomes cosine theta d theta j hat over r. So these are integrals that you can evaluate, and I am going to need some space. So I will clear up some space to finish this. But we're just about done at this point. And again, you expect, given the symmetry, that the x component will go to 0. But let's prove that it does. So you have the negative, and it's the negative sine over theta. But if you integrate the negative sine over theta, you get a cosine. So that becomes lambda over 4 pi epsilon naught. And we're going to bring the r term out now. And so let's look at this. So the integral of the negative sine of d theta is equal to the cosine of theta. So that's the cosine of theta I hat. And you're evaluating that from negative pi over 2 to pi over 2. And then plus the sine theta j hat, again, evaluated in the same way. So the cosine of pi over 2 is 0. The cosine of negative pi over 2 is 0. Remember, pi over 2 is 90 degrees. So again, you see that mathematically you can verify that the component in the x direction cancels out, that you have positive components on the left side, negative components on the right side. They all cancel out. So there's the net electric field only points in the j hat, or the positive y direction, so directly up and out from the wire. So that's lambda over 4 pi epsilon naught r, and the sine of theta is 1, and you're subtracting that, or the sine of pi over 2 is 1, and you're subtracting from that the sine of negative pi over 2, which is negative 1. So that's 1 minus negative 1 is 2. So you can write that as 2 j hat, or simply lambda over 2 pi epsilon naught r j hat. So this is the magnitude of the electric field, and so it varies, or it decreases inversely with r, the distance you are away from the wire. And it's in the j hat direction, which means directly out of the wire. So it's coming from the wire, from the closest point in the wire to where the point is being evaluated, where the field is being evaluated. And, it's going directly that way. So the j hat direction, the y direction. And so that's how you solve that integral. And that was complicated. We had to clear out the whiteboard a little bit in order to solve it. But now let's see how that looks with Gauss's law. So you have your long straight wire. You're looking at a perpendicular distance r away from the wire. And so you're evaluating the electric field at this point P. So how would you solve this using Gauss's law? And once you see how I solve this using Gauss's law, you're probably going to get mad at me for showing you the integral. But here's how it looks. What we do is we construct a Gaussian cylinder. So it doesn't have to be an actual tangible cylinder, but a Gaussian cylinder of length L and radius r. So the length L is arbitrary. You can make the cylinder as big or as small as you want, but you're evaluating at a point r. And so so the cylinder has to have that radius value of r. So what do we know? Well, we could figure out intuitively that there's not going to be an x component to the electric field, which means on the circular faces of the cylinder, there's not going to be an electric flux. But on the round face of, the rounded portion of the cylinder, there is going to be an electric flux. But again, given the symmetry of the problem, you know that, again, if there's no x component, that means the electric field is going to be pointing out, directly out of the cylinder at all the points on the rounded portion as opposed to the flat circular faces. But it's going to be pointing out of the cylinder at all those points. And if the cylinder is centered on the wire, so that the wire is on the axis of the cylinder, all the points on the surface of the cylinder are going to be the same distance away from the wire. So the magnitude is going to be the same. It's going to be a magnitude E. And so the electric flux is going to equal E multiplied by the surface area of the rounded portion of the cylinder. So what is that? That's equal to the circumference of the circle, 2 pi r, times the length of the cylinder L. And so that's going to, from Gauss's law, that's going to be the length of, or rather, from the definition of the electric flux, that's going to be the electric flux through the cylinder. From Gauss's law, that's going to be equal to the total charge enclosed within the cylinder, which is just the portion of the wire that's within the cylinder. But that's equal to lambda times L divided by epsilon naught. And so we've set up an algebra equation. The length of the cylinder is arbitrary. And so we just solve this for E. E is equal to lambda divided by 2 pi r epsilon naught. As simple as that. Much fewer steps, much less time than the last one, or than doing it by brute force integration. But that shows you, one, how to evaluate an electric field integral, but two, how Gauss's law works and how powerful it can be. And so we've done this with one dimension. Now we're going to up the ante a little bit and look in 2 dimensions. Well, before we do that, we'll go to a simpler, we'll do a simple example, and then we'll move to 2 dimensions. So a long, thin wire, hundreds of meters long. And so when we say an infinite length of wire, obviously there's no such thing as an infinite length of wire, but if you're evaluating the electric field close enough to the wire so that the ends of the wire are contributing nothing or a negligible amount, then the infinite length of wire approximation holds really, really well. And so the long, thin wire, hundreds of meters long, carries a uniformly distributed charge of negative 7.2 microcoulombs per meter of length. So we're given lambda, and lambda is negative. So that's going to tell us the electric field is pointing in to the wire. So estimate the magnitude and direction of the electric field. We've already figured out the direction. At points 5.0 meters and 1.5 meters perpendicular from the center of the wire. So let's go back to the board, and I did not erase anything, and I'm not going to. So we know that lambda is equal to negative, was it 7.2 microcoulombs per meter. So we're given lambda, and so for A, we have the electric field is equal to, and so that's negative 7.2, and we'll write it out in scientific notation, times 10 to the negative 6 coulombs per meter, divided by 2 pi, divided by the radius, and so we're told in this case that it's 5.0 meters away. So it's 5.0 meters, and then epsilon naught is 8.85 times 10 to the negative 12 coulombs squared per Newton meter squared. And so we will get an answer in terms of newtons per coulomb. So what we get is 2.59, or it's two significant figures, so 2.6 times 10 to the 4 newtons per coulomb. So that's part A. And then part B, we're getting closer to the wire, so you expect the electric field to be stronger. And everything else is the same. And don't forget the negative sign, and the negative sign means the electric field is pointing in to the wire. Times 10 to the negative 6 coulombs per meter. And this time it's 1.5 meters, so we're closer. But otherwise, it's the same calculation. Okay, so here you get 8.6, and again, don't forget the negative, 8.6 times 10 to the 4 newtons per coulomb. So it gets stronger as you get closer. And again, the negative means that the electric field is pointing directly in to the wire. Okay, so that's a basic example of how to apply this in the case of a line charge. But like I said, now we're going to up the ante a little bit. And so now we're going to look at an infinite plane of charge. And this actually has a very important practical application that we'll talk about when we see the results. And again, there's no such thing as an infinite plane of charge, but if you're close enough to the plane or to the sheet of charge that the electric field at the edges is negligible, then it's functionally infinite, or the infinite plane approximation works well. And we'll see that results in a fairly important application. So let's take a look at this. And we will write it out. And again, we'll do it the long way first. I'm assuming you have enough experience with integrals that if you have enough experience with integrals, that if if I show you a two-dimensional integral, at least integrating over a rectangle, you won't be lost by that. Well, we'll take a point at the origin, and so we'll call this the head-on view. And so it's the origin, at least relative to the sheet. So it's in the XY direction like that. So the sheet is in the XY plane, and then the side view some people are better at drawing three-dimensionally than I am, but I prefer multiple views than to try to make it look good in a three-dimensional perspective. And we'll say we're a distance z away from the sheet. So we'll do it like that. And so you have the electric field in this case, again, is equal to 1 over 4 pi epsilon naught. And that's dqs. And again, 1 over 4 pi epsilon naught is simply the Coulomb constant. And then that's r cubed. And so with that vector. So we're going to need to figure out the differential element of area, and then the r vector. What's the what is the vector from an infinitesimal element of charge to a point on the to the point P where the field is being evaluated. So we will so we have our infinitesimal element of charge here on the sheet, and so we'll draw it there as well on both faces. And remember, the vector points to the point where the field is being evaluated. So how does R look? Well, we know that this, well, first let's do dqs. dqs is equal to this charge density sigma divided by the, or multiplied by the element of area, which is dx dy. So again, it's two-dimensional. So the charge density, the charge per unit area, multiplied by the differential element of area. And then we want our r vector. So what you see from the r vector, again, if you're to the left of the origin, it points to the right. If you're to the right of the origin, it points to the left. And if you're above the origin, it points down. But if you're below the origin, it points up. And so, and that's in the y direction. But then if you include the z direction, it's always going to point in the z direction. There's always going to be a component in the z direction, and that component is equal to the distance z. So you can write r as being equal to negative x I hat. So again, if you're to the right of the origin, the vector points to the left. Minus y j hat, because if you're above the origin, the r vector points down. If you're below the origin, the r vector points up. But it's plus z k hat. So you're always pointing out you're defining the positive z direction as the direction to point P. You're always pointing out. So you have that. Now, the magnitude of r is equal to x squared plus y squared plus z squared. And again, that comes from the Pythagorean theorem. And if you're talking about the squares, the fact that x and y are, the fact that you have negatives here doesn't matter. So now we can set this up. And so you have sigma dx dy over, and again, it's a double integral. So in both cases, you're going from negative infinity to positive infinity. And so you have negative x I hat minus y j hat plus c k hat. And all that divided by, and you get a similar looking integral to last time. It's x squared plus y squared plus c squared to the 3/2 power. And so that's the integral we're going to solve. I'm going to cheat a little bit, however, for the sake of time constraints. If you look in the x direction, half the terms are going to wind up, half the time you're on the left and the x vectors are going to point to the right. Half the time you're on the right, the x vectors are going to point to the left. The x terms are going to cancel out. Similarly with the y direction. But in the z direction, they're all going to point out of the surface towards point P. So we could do the integrals for x and y, but they go to 0. If you want to do that as an exercise on your own, you can. But it's ultimately not going to change your results all that much. It's not going to, it's not going to change your results at all, actually. So we'll write this simply as E is equal to 1 over 4 pi epsilon naught and so we're integrating twice from negative infinity to positive infinity. And so that's just, and we'll put the sigma out. In fact, we'll put the z out as well because it doesn't come into play in the, it's a constant term. And so we have dx dy k hat over x squared plus y squared plus c squared to the 3/2 power. So we're going to need another substitution to solve this. So we'll define a value let A equal x squared plus y, the square root of x squared plus y squared, so that x is equal to a times the cosine of theta, and y is equal to a times the sine of theta. So that what we're going to do then is we can write this as, instead, because it's infinite sheet, the geometry doesn't actually matter. That an infinite circular sheet and an infinite rectangular sheet will give you the same results. And so that's a bit of a mathematical trick to this, is that if the dimensions were finite, the geometry would matter. But because the dimensions are infinite, the geometry doesn't matter. Then you get a far enough distance away, and the edges aren't going to contribute anything meaningful. So you can write this. So the answer is the same whether it's a rectangular sheet or whether it's a circular sheet. If it's infinite, you'll get the same answer. So let's treat this then as a circle of radius a, so that dx dy becomes a times dA d theta. So we're changing the infinitesimal area of a rectangle to the infinitesimal area of a circle. And so then what you get for E, so again, just to summarize what I'm doing, I'm making a substitution. I'm treating it, instead, because it's an infinite sheet, I'm treating it as though it's an infinite circular sheet as opposed to an infinite rectangular sheet, because the answer won't actually change. Again, because you get far enough away that the edges, as the distance goes to infinity, the contribution to the electric field goes down to 0. So beyond that point, the shape doesn't matter. And so E is then equal to, and again, we have sigma z over 4 pi epsilon naught. And that's, we're going to integrate over the full circle. So that's from 0 to 2 pi. And then the radius goes from 0 to infinity, or the radius of the circle goes from 0 to infinity. So we have a dA d theta in the numerator, and that's k hat, that doesn't change, over this term, which becomes a squared plus c squared to the 3/2. All right, I'm starting to write tiny. All right, so we're still going to need another substitution. So we're going to let u equal a squared plus c squared, so that du is equal to 2a dA. So again, we're doing a substitution here. And so the differential of u is equal to 2a dA, so that a dA is equal to du over 2. So now let's erase, give ourselves some space to work with. And again, setting up the integral is the hard part, actually doing the integral less so. So we have E equals, so that's sigma z over 4 pi epsilon naught, and we'll bring the unit vector out here. So that becomes 0 to 2 pi. And then we'll put the d theta term here. Notice there aren't any theta dependent terms. So this integral is just going to become 2 pi. And then over here, we have du over 2. Don't forget this term. And then that's u to the 3 halves. And so u starts when a is equal to 0, u is equal to the square root of z. So you have to include that term. So you're integrating from the square root of z, and then when a goes to infinity, that goes out like that. Or rather, when a is 0, u is equal to c squared, excuse me, or z squared. So let's work on this a little bit more. So this term becomes 2 pi. So we can write this as sigma z over 2 epsilon naught. And then you're integrating du over u to the du over u to the 3 halves. So let's erase this side so we can show how that integral works. So you're integrating du over u to the 3 halves. So and we might as well keep the 2 in there. So du over u to the 3 halves. So that's the integral of du times u to the negative 3 halves over 2. Just writing it like that. And so that becomes 1/2. And so that's from z squared to infinity. So that's 1/2. And then u is the integral of u to the negative 3 halves is u to the negative 1/2 over negative 1/2. And you're integrating that from z squared to infinity. So you have negative, bringing this negative out, u to the 1/2 over 2 times 1/2, so that's just 1. And you're integrating that over z squared to infinity. And so you can write that as the negative of the square root of u from z squared to infinity. So, or rather, negative 1 over the square root of u. So u to the negative 1/2 is equal to 1 over the square root of u. So this becomes negative 1 over the square root of u from z squared to infinity. 1 over the square root of infinity is simply 0. So that's negative 0 minus, and then 1 over the square root of z squared is 1 over z. So that term, that just equals 1 over z. So the theta integral becomes 2 pi, and then the u integral becomes 1 over z. And so that goes here, and that's all in the k-hat direction. The z terms cancel out, and that's an extremely important consequence, so that the electric field is equal to sigma over epsilon naught, or rather 2 epsilon naught, k hat. The z term drops out, so what that means is that the electric field doesn't actually depend on distance, that if the sheet is infinite the electric field is uniform. The magnitude does not change. And again, there's no such thing in reality as an infinite sheet, but if you're close enough to the sheet or to the surface of charge so that the edges of the sheet contribute negligibly to the electric field, then the electric field is essentially uniform in that region. And that makes it possible to create a uniform electric field. And so that's an important laboratory. In a laboratory, if you want to create a uniform electric field, this is how you do it. You create a big sheet of charge, and you keep your charged objects, or you're evaluating the electric field, close to the surface and far enough away from the edges so that the edges don't matter. And then in that area where the edges don't matter, the electric field is uniform, or at least approximately uniform. So that's how you do it using integration. Again, many, many steps. How does it look with Gauss's law? So we can establish again that, just from qualitative analysis, that you're looking at a point P away from the surface, that the X and Y contributions cancel each other out, and so that you have a field that points out, and you're a distance c away from that field. So what you can do is draw what's called a Gaussian pillbox. So where point P is on the outside, and it could be a cylinder, it could be a rectangular prism, it doesn't actually matter. The only faces where there's going to be a flux are going to be the face where point P is, and then the opposite face on the opposite side. And that the sides that are parallel to the electric field are going to have no flux. So the electric flux then, and so we have, we'll call it a Gaussian cylinder of cross-sectional area A. And in the last example, the flux through the flat faces was 0. Here, the flux through the rounded side is 0, but the flux through the flat faces we can evaluate. And so, again, on this surface, the electric field has to be equal. If you're the same distance away from the surface, the electric field has to equal or has to be constant, and it has to be uniform. It's pointing out. So we know that the flux is equal to, so you have the electric field multiplied by the cross-sectional area A. So the electric field going through this flat surface multiplied by its cross-sectional area, but you have a mirror image, so you have to take into account the flux on the other side as well. And remember, the electric field is always going to point out if you've got positive charges on the flat surface. So whatever charge you have here, if it's pointing out at this surface, it's going to point out at this surface as well. So the total area is 2 times the cross-sectional area. And because you need to count the area of both sides, times E. And that's equal to the enclosed area, which is, or the enclosed charge, which is sigma, the charge per unit area, multiplied by that cross-sectional area and divided by epsilon naught. And so the magnitude E then the A terms cross out. So it doesn't matter how big or how small you make that the area of the Gaussian cylinder. You divide both sides by 2, you get sigma over 2 epsilon naught. So you see how easy that is as opposed to doing the integration by brute force. But to get the same result, and again, it's an important result, it shows you how to create a uniform electric field, or at least an approximately uniform electric field. And again, it's going to point, if the charges on the sheet are positive, it's going to point out, the electric field is going to point out from both sides. If the charge on the sheet is negative, it's going to point in from both sides. But again, Gauss's law making a very complicated problem look very simple. So, or turns a complicated integral problem into a simple algebra problem. And that brings us to spheres. Now, we're not going to go through the integration of the spheres, but we can show how Gauss's law simplifies the problem. So we're going to look at 2 types of spheres to start with. A uniform sphere and a uniform spherical shell. So the uniform sphere so you have charge throughout the sphere. Now, an important property of conductors is that the charge accumulates on the surface of a sphere. So you can't have a conducting solid, sphere where the charge is distributed throughout. A spherical shell can approximate a conductor, but for the uniform sphere, that is not the case. And so we have of charge Q. And so again, the charge is throughout the sphere. And so we'll say the sphere has a radius capital R. And so we want to find, in fact, what I'm going to do, let's get rid of those lines. So we want to find the electric field both outside and inside the sphere. So we'll start inside. Outside is easier, but it actually is the more important concept. So I want to build up to that. So you have a charge uniformly distributed within the sphere. And like I said, a conductor would not have that. So we are going to draw a Gaussian spherical surface of radius small r. Of radius small r. So we look at the symmetry. At any point on the surface of the sphere, you would expect the electric field to have the magnitude of the electric field to be constant, assuming the center of the Gaussian sphere is on the center of the real sphere. That you would assume the electric field is constant because of the symmetry. So we can write the electric flux then as being equal to E, and that depending on the magnitude of the charge, if you're talking about a positive charge, the electric field is going to point outward. If you're talking about the negative charge, it's going to point inward. But so the electric flux is equal to the magnitude multiplied by the surface area of the sphere, which is 4 pi times r squared. And that's equal to the enclosed charge divided by epsilon naught. But what is the enclosed charge? So how much, again, if the charge is uniformly distributed throughout the sphere, how much charge is in the Gaussian sphere. So Q enclosed is equal to the total charge which is just capital Q, multiplied by the volume of the Gaussian sphere. So that's 4/3 pi small r cubed divided by the volume of the entire sphere. So that's 4/3 pi capital R cubed. So this becomes Q times small r cubed divided by capital R cubed. And so we can write this as capital Q small r cubed divided by epsilon naught capital R cubed. And then we solve this for the electric field. So we divide both sides by 4 pi small r squared. And so what you get is Q over small r, or times small r. So you have r cubed divided by r squared. And divided by 4 pi epsilon naught capital R cubed. Let me write this a little better. And so what do you get from that? Well, that inside the sphere, the electric field varies linearly. So it starts at 0 in the center, and it increases linearly with radial distance. Now, what if you're looking outside the sphere? So what if r is greater than, or small r is greater than capital R? So what if you're looking at a point outside the sphere? Well, this is actually an easier case to evaluate. So it's E. The Gaussian surface is now fully encloses the surface where the charge is. So that's E times 4 pi small r squared. So again, you have a Gaussian surface, and you're taking the surface area of the sphere, but the entire actual sphere is within, so the enclosed charge is equal to the total charge Q. So that's Q over epsilon naught. So E then is equal to Q over 4 pi epsilon naught r squared. But remember, K, the Coulomb constant, is equal to 1 over 4 pi epsilon naught. So that becomes KQ over r squared. That's the same as the electric field due to an individual source charge located a distance r away from where you're evaluating the electric field. So what does that mean? That outside of a sphere, that the electric field is the same as it would be if all the charge in the sphere were located at a single point in the center. That relationship, it turns out that relationship applies to any spherically symmetric charge distribution, provided that you're looking at a point outside the sphere. So you could have any spherically symmetric charge distribution. So you could have alternating layers of positive charge and negative charge, or any sort of random distribution, provided that it's spherically symmetric. So, it's otherwise, you can have the charges distributed any way you want. But if you're looking at evaluating the electric field outside the sphere, or outside where the charges are, the electric field would be the same as it would be if all the charge were located at a point on the center. So now we're going to take the analysis a little bit further. We're going to look at a shell of charge. So all the charge on surface. So again, you have a radius capital R, and you want to evaluate the field at a distance small r away. So you construct the Gaussian surface just like before. Now here, the electric field inside the sphere has to be 0. You're enclosing no charge. And so from Gauss's law, that's telling you the electric field has to be 0. You could go through this with integration, and what you would find is that the components of the electric field cancel out in all directions. So if you were to evaluate the electric field due to the charges outside, they would all cancel out. And you'd be left with an electric field 0. And that'd be true at any point inside the sphere. And yes, you can solve this using integration, but that's a pretty hard integral to solve. Outside, just like before, with any spherically symmetric charge distribution, outside E is going to equal 1 over 4 pi epsilon naught Q over small r squared. So again, whether it's a spherical shell, a uniformly charged solid sphere, or any sort of spherically symmetric distribution, if you're looking outside the sphere, the electric field is going to be the same as it would be if all the charge were located at a point in the center. But in the case of a spherical shell, the electric field inside the sphere is 0. That has an important application when you're talking about conductors. The charge always accumulates on the surface. So if there's an extra charge on a conductor, it accumulates on the surface. And it will distribute itself so that E is equal to 0 inside. So the conclusion with the spherical shell can be extrapolated to any shape of shell of charge. And if it's a conductor, the charges will move on the surface until there is no electric field inside. And what you find with this circle or with the sphere can be generalized. And so that's an important practical application. So inside a conductor, the charge is always 0. And that brings us to one final example, and then we're done with this lecture. The field just outside a 3.50 centimeter radius metal ball, metal means conductor, is 6.25 times 10 to the 2 newtons per coulomb and points towards the ball. So we're outside the ball, so it's like all the charge it's the same as if all the charge were located at the center. And that makes this a fairly easy problem to solve. And what charge resides on the ball? Well, if the electric field is pointing in, it's a negative charge. So let's do this mathematically. So we can write this as E is equal to negative KQ over R squared. Again, we're outside the sphere, so it's like all the charge was located at a point on the center. And since the electric field is in, we can write the electric field as being negative if it points inward. And so the Q that we wind up getting is going to be negative as well. So Q is equal to negative E R squared over K. And again, we're writing E as negative because we're putting the negative sign in because E is pointing inward. So basically, the radial component of the electric field is negative. I'm not going to really get into too much detail with spherical coordinates in this course, But you can talk about a radial component of an electric field. And if it's pointing inward, it's negative. And so you write this as Q is equal to negative. The electric field is given as 6.5 times 10 to the positive 2 newtons per coulomb, or 6.25. And we can write that as simply 625. The sphere is 3.50 centimeters in radius. So in SI units, that's 0.0350 meters, and that's squared. And you're dividing that by K. So K is, to 3 significant figures, 8.99 times 10 to the 9 Newton meters squared per coulomb squared. And so we'll get a charge in units of coulombs out. And so that becomes negative 8.52 times 10 to the negative 11 coulombs. So it's not a whole lot of charge, but you can still evaluate the electric field. And you're not that far away from the center of the sphere. And so you're just outside. So it's 3.50 centimeters. And you can, if you were just inside, the electric field would be 0, because again, it's a metal ball, it's a spherical shell. So that's all for this chapter. So next chapter, we will introduce what's called electric potential and how that relates to potential energy. So thank you for watching this. And again, if you have any questions, feel free to email me. So thank you very much.